I know it feels like you're standing or sitting still right now, but the ground you're resting on is indeed moving. And I'm not even talking about the fact that our planet is just zooming around the sun at over 100,000 kilometers per hour. It's a slow movement that's responsible for building mountains and volcanoes and causes earthquakes. What is this slow movement and how do we know it's happening? Let's find out together in this episode all about plate tectonics. The ground below you is traveling across the Earth at a rate of about 10 centimeters per year, or about as fast as your fingernails grow. This motion is due to plate tectonics, or the large-scale movement of Earth's continents. Plate tectonics is the unifying theory that explains the past and current movement of rocks at Earth's surface, and provides a way for us to understand Earth's geological history. This idea that our planet's continents drift around the globe, slow motion, crashing into each other, and drifting apart is a relatively new theory. In fact, most geologists didn't accept it until the 1960s, when mounting evidence made it clear the Earth's crust is broken up into fragments, and that those fragments, called tectonic plates, are moving. It was a meteorologist named Alfred Wegener who first suggested that Africa and South America looked like they could fit together like puzzle pieces. I mean, they're thousands of miles apart and separated by ocean, but they really do look like they could fit together. So he just started basically asking, could these guys have once looked more like this? He did find geological and fossil evidence to support his claim, which led him to propose a controversial new theory. Perhaps these and many other continents had once been connected in a single, gigantic landmass. But Alfred had no idea how the continents drifted. He thought they basically just bulldozed their way through the Earth's crust. He was essentially booed so loudly by the scientific community at the time that he gave up and went back to studying the weather. But fortunately for us, the scientific groundwork had been laid. Continental drift became the foundation for our modern theory of plate tectonics, which states that Earth's crust is made of vast, jagged plates that shift over a layer of partially molten rock called the mantle. Scientists have documented evidence from various features on Earth, such as the fossil record and magnetic patterns in rock, and specific geological features that support the theory of plate tectonics. Scientists have found fossils from the same species on different continents. The same plant fossils and reptile fossils, like the Mesosaurus, can be found on the South American East Coast and African West Coast. This suggests that the animals lived when the continents were connected. The best evidence came by looking at rock in the oceanic crust. Earth's magnetic poles will switch back and forth occasionally. North will become south and south will become north. Sounds chaotic. That change gets recorded in rock. When molten rock cools during seafloor spreading, its iron-rich magnetic minerals are frozen, aligned with the current magnetic polarity. This process creates alternating symmetrical magnetic stripes on the ocean floor, recording reversals in Earth's magnetic field. The farther you get from the ridge, the older the rocks get. The youngest rocks are closest to the ridge. Then there are the locations of mountain ranges, deep ocean trenches, ocean floor structures, earthquakes, and volcanoes that occur in patterns. The exact patterns depend on if plates are being pushed together, pulled apart, or sliding past each other along surface faults. These geological features and events indicate where tectonic plate boundaries can be found. More on that in a bit. If you're still here, liking this video, let us know. And hit that subscribe button so you never miss an episode. Before we discover where plate boundaries are located and how they interact, we need to look at Earth's layers and what exactly the tectonic plates are. The Earth is made of several layers that go all the way down to its core. The top layer of the Earth that's doing all of this moving is called the lithosphere. This layer consists of the Earth's crust and part of the upper mantle. This layer makes up the tectonic plates, sometimes called lithospheric plates. Plates are divided into two kinds, oceanic and continental. Continental crust forms the continents and the areas of shallow water close to their shores, whereas oceanic crust forms the ocean basins. The continental crust is thicker, but less dense than the oceanic crust. As you continue toward the center of the Earth, the temperatures and pressures increase. This area has heated up enough to become ductile or plastic-like and can flow and bend. It's not quite a liquid, but also not a solid. Think of it like silly putty. Heat it up enough and it can move and bend. The asthenosphere is what those lithospheric plates are moving and shifting around on top of. If you need a refresher on Earth's layers, this video will help. The speed and direction in which these tectonic plates move depends on the temperature and pressure of the asthenosphere below. Mantle convection is the best explanation as to the driving force behind plate movement. Convection currents within the Earth's mantle, driven by heat from the core, are the primary mechanism causing tectonic plate movement. You can see this convection current in action. Our heat source is here in the middle. Hot mantle material rises toward the crust, moves horizontally, cools, then sinks. Easy peasy. This is a map of where the earthquakes are concentrated on our planet. Let's add volcanoes to the map. You can see that there is a large concentration in this area. This is known as the Ring of Fire. Let's overlay a map of the tectonic plates. Can you see a connection? There is a series of interconnected, highly active plate boundaries located here, which is causing the earthquakes and the volcanic activity. Because all these plates move independently, a fair amount of pushing and pulling between the plates occurs. We categorize the way that plates interact at their edges as having convergent, divergent, and transform boundaries. Let's take a look at where the Indian tectonic plate collides with the Eurasian plate. The crust of the plate becomes compressed, and the Indian tectonic plate gradually moves awkwardly under the Eurasian plate. Due to the lower density of the crust, the Indian tectonic plate doesn't sink back into the asthenosphere all the way. This action lifts up the Eurasian plate and creates the Himalayan mountains, some of the tallest in the world. This mountain range is home to Mount Everest, which is the tallest mountain above sea level. In fact, the two plates are still colliding, causing the Himalayas to grow by more than 1 centimeter each year. Another example would be on the west coast of the United States. Here we have a dense oceanic crust that is being pushed underneath the continental crust and begins to melt as it moves farther and farther down, eventually forming Mount Rainier and Mount St. Helens, which are active volcanoes. Old oceanic crust is constantly being recycled in subduction zones. This is where oceanic crust, being more dense, is subducted or sinks below the continental crust, where it melts and is recycled into the mantle. Divergent boundaries happen where two tectonic plates move apart. These boundary types can create different kinds of landforms, like rift valleys and mid-ocean ridges. North America and Eurasia were connected, but they're not bulldozing through oceanic crust to try to get away from each other. New oceanic crust is being made in the middle. The spreading is driven by that mantle convection that we learned about earlier. At the bottom of this beaker, I have wax to represent magma just under the crust. And on top of that is sand to represent a thin layer of oceanic crust. As the magma rises at the ridge, it creates new crust and pushes the older crust away. Two plates sliding against each other create a transform boundary. Slide isn't really the best way to describe it because the plates don't just move in a smooth, continuous motion. When two enormous rocky plates move past each other, there's a lot of friction. Basically, pressure builds up between the two plates. And once it becomes too great, the plates slip and release this pressure. This motion causes earthquakes. There are so many earthquakes in California because the San Andreas Fault cuts the state right in half. The Earth's surface is continually being shaped and reshaped by competing constructive and deconstructive geological processes. All those plates we just learned about are still moving, like right now. So the next time you look at a map and think, South America and Africa really do look like they fit together. Remember Alfred Wegener and his not-so-crazy ideas. And if you want to learn more science, you can check out this video next. I'm trying to teach about plate tectonics, guys. Okay, let's try it.